Hi, my name is Ross, and I'm going to be talking about the economics of each method, the environmental effects of each method, and an example of a plant combining both methods.
Hi, I'm Casey Holsh, and today I'm going to be talking about the efficiencies of reverse osmosis and multi-stage flash distillation plants.
Hi, I'm Michael Stevenson, and I'll be talking about the different types of reverse osmosis membranes and the size capacities and the locations of each type of plant.
Hi, I'm Mariah Tarpinian, and I'll be talking about the different methods of desalination.
Fresh water is one of the most important resources that we use every day in life. This can be a particular challenge, though, for countries with dry and arid climates. One of the solutions to getting more fresh water would be distillation, and particularly distillation of seawater, because seawater is one of the most abundant resources on Earth. Approximately 70% of our planet is made up of oceans. This seawater, though, cannot be used as it is. So to produce more fresh water, we can take this seawater and now use different types of distillation to produce this fresh water that we need. Though there can be many different types, the types we are focusing on are reverse osmosis and multi-stage flash distillation. Multi-stage flash distillation, or MSF, turns water into steam and then condenses it back into a product stream, while reverse osmosis, or RO, uses a semi-permeable membrane to remove large particles from the water to produce the product. Both methods have proven to be very efficient in producing fresh water from seawater, but which method to use is a topic that we're going to explore further throughout our presentation.
Okay, so we're going to begin by talking about multiple stage flash distillation. So MSF is a seawater distillation process based on the principle of flash evaporation. Flash evaporation is essentially when the incoming feed stream of seawater is heated and evaporated and then condensed to produce the distilled water. So the process operates in three distinctive steps: heat rejection, Bryn heating, and heat recovery. It begins with the seawater feed flowing through the heat rejection steps. This step is essentially an industrial scaled evaporator consisting of several consecutive evaporating chambers. The water flows through the tubes of the heat exchangers in each chamber, increasing in temperature after each consecutive stage. It leaves this step at a very high temperature and enters the Bryn heater. As the water flows through the Bryn heater, it reaches its maximum temperature. Then the last step is the heat recovery step, and that is when the stream leaves the heater and enters the heat recovery stage through a narrow tube, restricting its flow rate and reducing its pressure. Because the makeup stream had already reached its saturation temperature for a higher pressure, it becomes superheated and therefore flashes to achieve equilibrium with the stage conditions, releasing heat and giving off water vapor. This produced vapor is condensed back into fresh liquid water in the heat exchanger tubes at the top of each consecutive stage, continually lowering in pressure and cooling down, giving the product fresh water stream. The concentrated seawater at the bottom of the system's evaporation condensers makes up the Bryn stream. Alright, so this photo is just a more complex representation of the MSF process. So as you can see in the top right hand corner is the incoming seawater feed. So the feed passes through consecutive evaporating changes in the first section, and then as you see it when it leaves there, it splits into two streams. At the very top you can see the reject seawater stream, and then the other stream that continues on into the next system of evaporating chambers is called the makeup stream. And the reason for this is just to eliminate waste earlier on in the process and for better efficiency. So then the only other difference in this photo from the last one is that you can see in the bottom right hand corner there's a stream labeled R, which is the recycle Bryn. So this is just when the Bryn leaves the system, it splits into two streams. The reject Bryn is pumped back into the sea while the recycle Bryn enters back into the system, combining with the makeup stream when it leaves the heat rejection stage. This complex method of seawater distillation is subject to varying efficiencies due to the influence of multiple process variables, such as temperature of the seawater feed, the temperature of the Bryn, and the number of evaporation chambers in the system. These process variables have been proven to have dramatic effects on the performance ratio of the flash-based evaporation system, and it has been experimentally proven that when holding all other external and internal variables constant, the optimal process variables are a seawater temperature of 25 degrees Celsius, a brin temperature of 90 to 110 degrees Celsius, and a number of flash units ranging from 20 to 25. Alright, so now we're going to talk about reverse osmosis distillation. So reverse osmosis utilizes a semi-permeable membrane to retain the solid containing bacteria, varying ions from solutions, and undesirable particles on the pressurized side of a selective wall, allowing only the most sanitary molecules to pass through, thus achieving the potable water. This membrane technology is used on an industrial scale by applying a pressure that overcomes the osmotic pressure to transport that waste-depleted water through the membrane, which is a dense layer in the polymer matrix. The reverse osmosis system contains of 4 steps: pre-treatment, pressurization, membrane separation, and post-treatment stabilization. The incoming seawater feed undergoes a pre-treatment process where the solids are removed and the pH is adjusted. The pre-treated stream travels through a pipe to a high-pressure pump, raising the pressure of the steam to an appropriate operating pressure higher than the osmotic pressure. The stream then enters the complex membrane system where the semi-permeable membranes block the undesirable solutes containing dissolved salts and contaminated particles from passing through. The membranes are utilized in a variety of configurations, and the stream exits the membrane system as a pure freshwater stream. It enters the post-treatment step, receiving a pH adjustment and removal of remaining gas before exiting the stream as a purified water. Alright, so in this photo you can see the system at work. You see the seawater enters, it goes through its pre-treatment process where it has a pH adjustment, then it flows through the high pressure pump, then through the complex membrane system, exiting as a freshwater stream, getting its post-treatment before leaving.
Reverse osmosis has the ability to utilize over 10 different types of membranes, each with unique features. 2 different types of membranes are cellulose acetate membranes, or Ca membranes, and modified polysulfone membranes, or PS membranes. Ca was the first membrane material used for RO, and is still used in present-day RO plants, while PS is more modern development and is widely used in current plants. Factors to consider while comparing membrane material include hydrophilicity, pore size, and pH tolerance. Ca can be defined as a very hydrophilic material, while PS is only a moderately hydrophilic material. As for pore size, both Ca and PS have average pore sizes of 0.01 micrometers. A distinct advantage cannot yet be determined between the 2 membrane materials. The final factor, pH tolerance, is vital because several different types of chemicals and acids can be added throughout the pre-treatment stage of RO. It is important to have a membrane that can handle a wide variety of pH values. Ca has a pH tolerance ranging from 3.5 to 8.5, while PS has the ability to range from 1 to 13. It can now be observed that PS would be a better option as a membrane material. It is considered to be highly durable with immense mechanical strength, mostly due to its previously mentioned tolerance to both high and low pH values. The comparison of the RO and MSF desalination plants is remarkably complex when taking into account the wide variety of crucial variables. Each process can have very different incoming stream capacities depending on geographical location, intended use, and type of feedwater. While it is difficult to find data that incorporates all of these considerations, Chautauqua Water Technology Center provides a great look into the average capacities of each desalination technique. According to Chautauqua, MSF plants can have a capacity ranging from 23,000 to 528,000 meters per day, while RO design plants can range from as little as 100 meters per day to as big as 320,000 meters per day. It is important to note that this data is only applicable when seawater is used as the incoming feedwater. For this particular case, we will ignore the possibility of brackish feed because MSF rarely uses brackish water. It is also worth noting that RO is a much more flexible technology and could also be utilized with a brackish water feed stream. After all is considered, analyzing the data shows that MSF plants are capable of being designed with a higher capacity compared to RO plants, while RO plants are much more flexible as they can be designed to maintain a capacity as low as 100 meters per day. It is irrelevant to declare either method's capacities as better or worse, for each type brings its own advantages and could be applied to different situations. While both MSF and RO plants can be installed in a variety of places, both are most common in areas where potable water is not easily accessible. MSF plants can have been extensively used in the Middle East, North Africa, and the Caribbean. They are most commonly installed in the vicinity of saltwater bodies because they utilize these bodies to input a stream of salinated water, and later use these bodies to dispose of a highly salinated brine solution. RO plants can be found in Latin American nations, Caribbean islands, and the United States. Like other types of desalination plants, RO plants can utilize an input stream of seawater, but some RO plants located in Latin America utilize groundwater and other type of brackish water.
When deciding which plant to use for distillation, many things need to be looked at, particularly the efficiencies of each plant. While researching each type of plant, we found that reverse osmosis plants use about 8.5 kilowatt hours per cubic meter of fresh water produced, and that reverse osmosis plants consume no thermal energy. These plants can also produce a freshwater stream that contains around 500 parts per million of total dissolved solids, which is still high compared to levels of drinking water, but would be acceptable for types of irrigation and other uses that fresh water is needed for. In addition, we found the inlet water temperature for reverse osmosis plants can be around 32 degrees Celsius. So if the water being used is warmer than 32 degrees Celsius, it would have to first be cooled to around 32 degrees Celsius so that it can be used. This would require more energy. But another good thing about reverse osmosis plants is that the energy from the first pass can be recycled and used for more passes. Multi-stage flash distillation, on the other hand, uses around 4 kilowatt hours of electrical power per cubic meter of fresh water produced. This type of plant, though, requires additional fossil fuels to be used to heat the water to produce steam. So the overall power consumption on a multi-stage flash distillation plant would be around 25 kilowatt hours per cubic meter of fresh water produced. This method of distillation, though, can produce a product stream as low as 50 parts per million of total dissolved solids. And once the water is cooled, it would be usable for any type of irrigation or even consumption. Additionally, these plants can operate at much higher temperatures. Inlet water streams can operate up to around 96 degrees Celsius. This means no additional energy would be required to cool the stream down to a usable temperature, seeing it can accept such high temperatures. While comparing the efficiencies of each method, we see that the reverse osmosis plants require less total operation power. MSF, on the other hand, can operate with inlet temperatures up to 3 times hotter than RO can. This can be an important factor when you find out how warm the water temperature is that you are going to be using. Since an RO plant would need water to be cooled to around 32 degrees Celsius for operation, it can add to the total operation power required by the plant, which would add more cost to production. If the temperature of the water, though, is not a factor in which plant to use, then RO would have less cost due to the less operation power needed. Finally, what the fresh water needed is going to be used for can be the deciding factor in which plant is needed to be used. Seeing MSF can produce a more pure product that contains less parts per million of total dissolved solids in the fresh water that is produced compared to a reverse osmosis plant.
Each method requires different materials and techniques to generate potable drinking water from highly concentrated salt water. These differences translate into differences in costs between the methods. In order to compare, we will look at the cost of each method if the plants are located in the Middle East, an area familiar to desalination. We will assume the feed water is 35 degrees Celsius and contains 42,000 milligrams per liter of total dissolved solids, the salts that need to be removed. We will also assume that the plant will produce 32,000 cubic meters of water per day because of the assumptions made in another study. To start examining the differing costs between each plant, we see that each method both have costs of constructing the plant and general upkeep. Labor costs for both plants are considered as well. From here it starts to differ. Reverse osmosis plants require membranes. What kind of membranes used can change. Either way, these membranes are sensitive to the feed water solution's pH, oxidizing agents, and bacteria, so chemicals are needed to be added to treat the feed water. Lastly, in order to overcome osmotic pressure, energy is needed in the form of electricity. However, for multi-stage flash distillation, the materials needed are boilers and condensers. However, the massive costs come from the fuel needed to vaporize the feed water. Considering all the costs for each method, the cost per meter cube of water is $1.44 US per meter cubed for a multi-stage flash plant and $1.39 meter cube per water for a reverse osmosis plant, showing that reverse osmosis is the more cost-effective method. The environmental effects of desalination come from either the retrieval of feed water or the release of the brine solution into the ocean. When taking in feed water, organisms can be removed from their ecosystem. Where the effects start to differ between the plants is how the brine, or highly concentrated salt solution, affects saltwater ecosystems. The brine disrupts sensitive organisms, significantly reducing some of their populations. First, the dangers of reverse osmosis come from the added chemicals. These additives make the outlet stream more dense than water, thus it sinks when released into the ocean. The organisms at the seafloor suffer. However, for multi-stage flash distillation, the outlet solution is just at high temperatures rather than containing dangerous chemicals. This hot stream stays closer to the surface, so organisms in that vicinity are in danger. There are some suggested solutions to reducing the non-intended effects of desalination on the environment. First, for reverse osmosis, instead of adding disinfectants, alternatives like UV light could be used to kill bacteria, but more research is needed to look into this technique. As for the high temperatures, using cooling towers could give the solution time to reach a safe temperature. There are benefits to using reverse osmosis, and there are different benefits to using multi-stage flash distillation. These two processes could be combined in one plant in order to increase the output of clean potable water. There is a plant in India that does utilize both processes in order to produce 1,800 cubic meters of potable water per day through reverse osmosis, adding to the 4,500 cubic meters of potable water per day through multi-stage flash distillation. The plant considered both options, and there are added benefits to using both methods. As discussed earlier, the multi-stage flash distillation method requires significantly more amounts of energy than reverse osmosis through the form of heat for vaporization, but the total dissolved solids in the product water for multi-stage flash distillation is less than 50 parts per million. The total dissolved solids for reverse osmosis is around 500 parts per million and is not preferred for cost reasons. So, by utilizing both methods, the water is blended to get drinking water of 250 to 300 parts per million. Due to a geographical location with an abundance in a certain membrane material, the overall cost of this output water is $1.23 meters per meter cube of water, cheaper than the estimated costs of separate processes. Thus, a combination of the two methods is a more attractive option in certain areas of the world. The treatment of seawater to separate pure water, lacking in high amounts of total dissolved solids, is necessary in the modern world. For this reason, desalination plants are widely used. Two methods of desalination have been discussed and compared. Multi-stage flash distillation using vaporization and reverse osmosis using a semi-permeable membrane are both feasible methods of desalination. The location of multi-stage flash plants are predominantly in places where the feedwater source is the ocean, while reverse osmosis plants can also use the ocean for feed. Instead, they are generally used for brackish water sources that have a lower starting dissolved solid concentration. Considering the efficiency of each source, multi-stage flash distillation outputs a more pure stream of water than reverse osmosis, but the energy needed to vaporize the water in multi-stage flash distillation surpasses the energy needed to overcome the osmotic pressure in reverse osmosis. Translating into cost, reverse osmosis is generally cheaper than multi-stage flash distillation due to the need for a heat source. Desalination has different forms of environmental impacts, but both reverse osmosis and multi-stage flash distillation can introduce different dangers because of factors specific to their processes. Overall, both processes have their advantages and disadvantages when comparing them to one another. Because examples have already been seen, in the near future, it is possible to see both methods utilized in the same plant and attempt to exploit the advantages of each method. There will always be a need to increase the efficiency of desalination through, especially through decreasing energy consumption, whether that be maximizing the heat transfer from fossil fuels or switching to an alternative fuel source. It is true that desalination plants are a necessary means to provide the world's inhabitants with an alternative freshwater source, a step in defeating another global problem.